9.2 Similitudes and Similarity. Our objective is to perform a size transformation and similitude. A size transformation of the plane is defined as follows. Let O be any point called the center of the size transformation, and K be any positive real number called the scale factor. The image of any point A under the size transformation with center O and scale factor K is the point A prime, where A prime is on ray OA. And OA prime over OA is equal to K, the size transformation. Let's put this into action. So if K equals 1.5 and O and A are given, then A prime is found as shown. We've got our distance from O to A, right? And OA over O, and K is 1.5. So OA prime over OA equals 1.5. So that means that OA prime, the distance of OA prime, would equal to 1.5 times OA. So I'd measure OA, multiply it times 1.5, and that tells me where the A prime would be. Right? A prime is on the ray OA, and then we lengthen it. Now it's not always lengthened. It could be, K could be less than 1. Then it would shorten the line. Let's do some examples. In the figure, find the image of the point A for the following size transformations. The size transformation with center O, scale factor 3. Size transformation with center O, scale factor 1/2. Size transformation is center O and scale factor 1. Alright, so we would start with OA. The scale factor is 3. I'd measure OA and multiply times 3. That's OA prime. If it's 1/2, I measure OA. I divide it in half. That tells me that OA prime is half. And then if the size transformation is 1, the point doesn't move. A prime and A are the same size. In this first one, this distance is 1, this distance is 3, and so on. Alright, any questions there? No questions there. Okay? Properties of size transformation. Size transformations take lines to lines, rays to rays, and line segments to line segments. Just like with the isometries, right? Size transformation preserve orientation. They preserve ratios of distances. They preserve angle measure. They preserve perpendicularity. They take lines to parallel lines. And what that last part means about they take lines to parallel lines, in this, so this size transformation, AC over BC equaled AC prime over BC prime. Alright? So that I would take my size transformation, whatever that value is, AC to BC. Well, it's they preserve ratios. So the ratio of AC to BC is the same as the ratio of A prime C prime B prime, C prime. Those ratios would be the same. These angles would be the same. And this with this last part, size transformation, take lines to parallel lines. That's saying if we have BC here and we do this transformation, then BC B prime C prime will be parallel to it. AC will be parallel to A prime C prime. Right, got it? All right. Now let's see. Let's look at number 2. They didn't talk about orientation in the list of properties of when we had the isometries. Which ones preserved orientation? Which ones didn't? Which isometries preserved orientation? Yes.
The ones that preserved were translation and rotation.
Right. Translation, rotation preserved. Reflection, glide reflection did not. Very good. All right. So how do you do the size transformation? Is there a size transformation that takes RST to triangle R prime, S prime, T prime? If so, find its center and scale factor. If not, explain why. So what you're going to do is you're going to go draw a line from S to S prime, and extend that line. Then you're going to do the same thing from R to R prime and extend it. It should meet in the same place if it's a size transformation. And we do the same thing with T and T prime. They all meet at O. Its center would be O, this point. We found its center. Now, as far as the scale factor goes, okay, we've got when we go from RT prime to RT, we go up 2 over 1, right? And then we do it again, up 2 over 1. So that tells me it's RT is 1/2 of RT prime. R prime T prime is 1/2 of RT. We can do the same thing with the S. We've got S prime is up 1 over 2, and then go to S from. You can go from S prime, it's another up 1 over 2, or you can do from O to S, that's up 2 over 4. Right? So we go from up 1 over 2 to up 2 over 4. That's 2 times. And S prime, T prime. From O to T, we've got from O to T, we've got up 2 over 1. From O to T prime, we've got up 4 over 2. So anyway, we've got R prime T prime over RT equals S prime R prime over SR, and equals S prime T prime over ST. It's a 1 to 2 ratio. 1 to 2 ratio. And O is the center. So the scale factor is 1/2. Now when you do the scale factor, put the prime numbers on top. The prime distances on top. R prime T prime is the prime. That's the result. That's the image, not the pre-image. So you put that on top and then the original on the bottom. So it's 1/2. It's not 2. It's 1/2. All right. Everybody think they can figure out how much it's changed the size transformation is? Any questions on doing that? Everybody see how I did it? I used slope. I saw the slope was doubled. So I said, okay, so it's a 1-to-2 ratio. Any questions? All right. So a similitude is a combination of a size transformation and an isometry. Similar triangles and similitudes. If triangle ABC is similar to triangle A prime, B prime, C prime, if and only if there's a similitude that takes ABC to A prime, B prime, C prime. Let's look at an example of a similitude. So, in this example 9-9, we've got, suppose triangle ABC is similar to triangle DBE. Find the similitude that takes ABC to DBE. Note, we can express any similitude as a composition of a size transformation followed by an isometry in infinitely many ways, depending on what point is chosen as the center of the size transformation. Although there is only one similitude, there are many different ways to describe it. So on this one, what we would do is the ratio of, let's take a look. Yeah. So we start with this original figure. We see the ratio of BE to BC is 8-to-5. Right? So I'm going to multiply BC times 8/5, and that's going to tell me where C prime is. And I do the same thing with AB. I multiply it times 8/5 and then make it that length, and so on. Then the image under the size transformation with center B and scale factor 8/5 is A prime, B, C prime. Right? Now, so once we transform the size first. Now, to get down to BED, we would have to reflect with respect to this line L. We would draw on this line of reflection, and then this point reflects here, this point reflects here, and that stays the same. So it would be a reflection with respect to line L. That's how we go from ABC to DBE. So my similitude was a size transformation of 8/5 followed by a reflection across the line L. Any questions? So you have to name what happens in the similitude. Let's do an example. So prove that any two squares are similar. So we're going to say that we have this ABCD, and we're going to do a similitude to make it EFGH. Right? We're going to say that the S the S corresponds with the T. We'll do it that way. Alright? So we know that, if we lengthen these lines, A prime, then this would be, that length, since it's a square, all the sides are the same. The length of the sides that I would lengthen the lines to would be t. Right? So I've got my scale factor is t over s. Right? I wouldn't multiply times t, I'd multiply by t over s. S times t over s equals t. That's how I got this t. Alright? And then what do we do to make it to be like EFGH? What is what's the isometry that I do after the size transformation? What do I do? Isometry? Yeah, which one? Yeah.
Rotation.
Yeah, it's a rotation. So this is a combo of a size transformation and an isometry. Which is a rotation. All right. Any questions? All right, in the last statement there, we've got similar polygons and similitudes. Two polygons are similar if and only if there's a similitude that takes one to the other. All right. So if they're similar, there's going to be some type of similitude. All right, any questions on the notes?